Hey guys, Mr. B here, and this is going to be a two-part video. So this first part is going to be the 3.1 notes, and in this section we're going to be talking about accuracy, precision, and error. And then in the second part of the video we will be going over significant figures. Section's a little bit longer, so figured breaking up into two parts makes it a little bit easier to watch rather than sitting down and watching it for 40 minutes. So, all right, let's get started here. So this section we're going to learn about measurements and how, of course, they relate to chemistry. So starting off, first, let's make sure we understand what a measurement is. A measurement is a quantity, so of course a number, that includes both a number and a unit. Okay, and the key part here to remember is the unit. Okay, do not forget your units when you're writing down your measurements. I know it's very common to just write down numbers, but don't forget the units. It's going to be very, very important later on in this course. This chapter, as well as later on, when we start getting into a lot of math stuff, the units are important. Okay, so don't forget that part. Obviously, our measurements are very important, especially in experimental sciences like chemistry, because a lot of calculations and things like that rely on our measurements. And so we need to make sure that they're good, they're correct, they're accurate, things like that. So we are going to, of course, be dealing with scientific notation in chemistry. If you're not familiar with scientific notation, you should have learned about it last year in 9th grade, probably with me, otherwise in previous years. But real quickly, scientific notation is a shorthand way of writing a really large or really small number. It usually involves taking the big number and reducing it so that it's a number between 1 and 10 times 10 to some power. Okay, so the example here they show is 200 million or billion, I think 200 billion. And there's a decimal at the very, very end. They move the decimal so that it's between the 2 and the first 0. So it becomes 2.0 or just 2. And then they count how many places that to move the decimal over, and that becomes the exponent. So in this case, this number 200 billion becomes 2 times 10 to the 11th. If this number were a really small number, like 0.000002, then the exponent would be a negative number rather than a positive one. Okay. If you need practice with scientific notation, there's some videos you can watch to get practice on it. But at this point, I assume you know how to do scientific notation. All right. So getting into the main part of this section, let's talk about accuracy, precision, and error. So accuracy and precision are two words that are very closely related to each other, but they are different. Okay. Accuracy is typically a measure of how close you are to a value that you're trying to get. So example would be, let's say that I went to the doctor's office. They took my weight and I weigh 149 pounds. Then I go home and I step on my bathroom scale. I would expect my bathroom scale to tell me 149 pounds. And instead, my bathroom scale tells me 145 pounds. So that would tell me the accuracy of my bathroom scale. The value that I should be getting is 149 pounds. The value that my bathroom scale is telling me is 145. So if I can compare what I'm getting compared to what I should be getting, that can tell me how accurate I am. Okay. As for precision, precision is more about a measure of how close multiple measurements are to each other. So it's more about consistency. So to be precise, you need to make 2 or 3 or 4 or more measurements, and they would all need to be close to one another to tell you precision. Okay. The other way also the precision is measured is with how many digits you are confident in reporting. So let me write this down. So this is or how many digits you are confident in reporting. Okay. So the example I have for you is here. Let's imagine that I have 3 scales and each one measures to a smaller number. Okay. So like for example, scale 1 is just a rinky-dink scale I bought at like Walmart or something, and it measures the whole number. So I step on it, it tells me 145 pounds. Okay. Scale 2 is a little bit of a nicer scale, costs a bit more money. I step on it and tells me 145.3 pounds. Then, of course, I go to the doctor's office, and they have a really nice scale that like measures down to like 1/10 of a pound or 100th of a pound. And this scale tells me 145.34 pounds. Okay. As we add more digits that we are confident about, that increases our precision. Okay. So this first measurement of 145 pounds is the least precise, and this measurement of 145.34 pounds is the most precise. Okay, so precision is about lots of measurements that you make and if they're close to one another, as well as how many digits are you confident in reporting. That also increases your precision. Okay, so just real quick, again, recap. In order for you to determine accuracy, you have to have a value that you measure and compare it to a value that you know is correct and see how far off you are. In order to measure precision, you need to look at 2 or more measurements and see how close they are to one another, okay? As well as, of course, how many digits you're confident in reporting. So this just shows, this image is of throwing darts, kind of shows this whole idea. This first picture shows good accuracy and good precision. We have good accuracy because the place that we're trying to hit is the bullseye, and we are hitting the bullseye, so we are accurate. And as for precision, we're throwing 3 darts, and they're all landing in the same spot. That means also good precision, okay? So they're landing in the same place, and they're hitting the spot they're supposed to be. The second image here shows poor accuracy, but good precision. Accuracy is poor because we're trying to hit the bullseye, and we're not hitting where we're supposed to be, okay? So we're far off from the actual mark we should be getting. But our precision is good because we're hitting in the same place every time, okay? So we have good consistency. And the third image here shows neither good accuracy nor good precision. Not only are we not hitting the bullseye, but we're also not even hitting in the same spot every time. We're all over the place, okay? So, all right. And the last part here we're going to talk about is error. So what is error? Error, of course, is how we determine how far off we are, or essentially how good our accuracy is. So to determine our error, we need to have an accepted value, which is the correct value that we're trying to get. Usually this is going to be based on reference tables or some number that we already know we should be getting. Our experimental value, which is usually the value that we then get ourselves, that we are measuring in the laboratory. And the difference between those two values is what we call our error, okay? So we would usually take our experimental value minus our accepted value, and we'll get our error. Now, our error can be positive and it can be negative, okay? It is possible to have a negative error. A positive error would just mean that we are over, okay? So positive error means that we are over, and a negative error means that we're under. So again, you know, if I step on a bathroom scale and it says 145 pounds and it should say 149 pounds, my error is going to be -4. The scale is under by 4 pounds. If I step on a bathroom scale and it said 153 pounds when it should say 149, then my error would be +4, meaning that the scale is over by 4 pounds. Okay, so it's okay to have a negative error. It just means that you're under versus you're being over. Now, the other thing, however, is instead of just giving error, we can also use what we call percent error. And the primary reason why we use percent error is because percentages are easier to understand than than other things. People understand percentages very well. So if, for example, I, stepped on a bathroom scale and or let's say, for example, I was doing an experiment and someone wanted to know what my error was. And I said, my error was +10. They would go, is that good? Is that bad? Is that too large of an error? I don't really know, right? Without more context, it's kind of hard to understand if that error is good or bad. Versus if someone said, well, what was your error? And I go, oh man, I was 50% off. They'd go, wow, 50% off, that's a lot. I mean, that's easier to understand. I don't need to know more context because 50% off is like, wow. If I said, oh yeah, I was 100% off, they go, wow, that's really bad. You were 100% off? That's crazy. You should probably redo that. So percent error is just easier to understand. To find your percent error, you take the absolute value of your error. So if your error is positive or negative, it doesn't matter. You just take it as a positive value, divide it by your accepted value, whatever you're supposed to get, times it by 100 to get your percentage. Now, as to what percent error is acceptable, it depends on what you're doing. Okay, so typically I would say any percent error that is less than 5% is completely acceptable. You can have a percent error up to 10%, and it can still be okay. It just depends what you're doing. So if you're doing an experiment where it doesn't really matter how close you are, then 10% error is probably fine. However, if you're doing something where it really requires really close numbers, then a 10% error could be way too far off. In fact, even a 1% error could be too far off. So it really does depend on what you're doing in the context. But either way, we'll be looking at percent error. So here's an example here where let's say that we were using a thermometer to measure the temperature of boiling water. So we put the thermometer in the water and our thermometer says 99.1 degrees Celsius. And we know based on reference tables that water boils at 100 degrees Celsius. So if we take our experimental value, which is the value that the thermometer is telling us, minus our accepted value, the value that the water should be, and subtract the two, we'll get an error of negative 0.9 degrees Celsius. However, if we want to find our percent error, we would take the absolute value of that, so positive 0.9, divide that by 100 degrees Celsius, and then times 100%, and we'd find that our thermometer has a percent error of 0.9%, which, to be honest, a 0.9% error is pretty good. So that's probably acceptable. Granted, it doesn't say exactly 100 degrees, but it's pretty close. It'd be acceptable, okay? Now understand, and the last part here is, just because you have a device that works doesn't mean that it is accurate. So especially in like the chem lab, when you are using the scales to take weights and like put things on there and read how many grams it is, a lot of students will forget that they need to zero the scale first. So what will happen is someone will use the scale before them, they'll take their stuff off, and they'll just put their stuff on the scale, read the number, write it down, and move on. And the problem with that is if you don't zero the scale, the number you're getting is going to be wrong. So in this picture here, this person is standing on a bathroom scale and it says about 118 pounds. But if you look at the image before they were on the scale, we'll notice that the needle isn't on 0. The needle's already sitting at about 4 pounds, or sorry, about 8 pounds. So that weight that the scale is telling them is incorrect, because the scale, even though it works, wasn't zeroed properly before they stood on it. Therefore, the number they're getting is wrong. Okay, so be very aware that just because equipment works doesn't mean it's going to give you the right answer. You do need to be aware that there is calibration that is required, and you need to zero things before you use them. Otherwise, you'll get inaccurate readings. Okay, so that is it for this first section of notes. The second part of this video will be on significant figures, which is a much larger section. Okay, so there's a whole video of me going over the first half of the practice problems in this section of notes, and then there'll be a video of me going over the second half as well as those practice problems. All right, guys, that's it for this one. I'm Mr. B. If you have any other questions, make sure you can email me. You can talk to me in person in class. We could always do Google Meet. But otherwise, I will see you in part 2. Bye.